Let us switch to our final speaker, Elisabetta D'Anastasio. Um, um, Dr. Elisabetta D'Anastasio is the technical lead of the science operations at GNSS Science, New Zealand, which operates the National Geological Hazards Monitoring Network, or GeoNet. She is also an appointed member of the governing board, of the International GNSS. Take it away.
Tēnā koutou katoa, and thanks a lot to Leo, the IGS Governing Board, and John Lebrecht for inviting me and giving us the opportunity to show what we use GNSS, how we use GNSS for natural hazards in Aotearoa, New Zealand. Before I start, I would just like to acknowledge and send my thought and aroha, which means love in Maori, to all the population that has been affected by the Turkey earthquake. And the numbers are impressive. Those figures are how us as scientists represent those tragedies, and I'm pretty sure that all of us share these thoughts, and all of us are doing the work we do to reduce these tragedies. The strategies are not new. Many of the other presenters before me today has already mentioned the Sumatra earthquake in 2004 and how impactful that was, and how a different and a better application and the knowledge that we have today on how we could use GNSS data would have possibly prevented such tragedies and so many loss of life. This is the talk I'm going to give today is mostly focused on the GNSS applications that are more closer to seismological applications. So I'm pretty glad that all the presenters before me has shown how the more novel applications, such as the ionosphere monitoring, can contribute to tsunami early warning. I will probably take a slightly different angle today. So the figure here is showing a paper from Geoff Blewett in 2005, and to the best of my knowledge, that's the first one that was showing how using GNSS station from the IGS network at the time and the 30-second sampling rate and some coseismic offset calculated rapidly would have been helpful to understand the magnitude and size of the Sumatra event. What happened at the time is that the classic seismological techniques were not able to estimate the real size and magnitude of the earth and of the earthquake and the impact and the magnitude of the tsunami that earthquake caused. And there is an article that I found cited by Blewett, which was trying to explain why some international global monitoring center has failed to understand the size of the earthquake. And I quite like the caption of this figure, the wiggles knew. So there are data around that will help us in reducing the time that we take to understand the real size of an earthquake. So after that paper in 2004, fast forward today, there's been many papers and a number of literature that others before me have already mentioned today, so I don't want to reiterate that. But the application that is closer to the seismological way of understanding earthquakes is using classical positioning techniques for GNSS data, using kinematic approach. So you estimate the position and the displacement every epoch, and every sample of GNSS data you have available, in this case, are 1 second data. And with that, you can estimate what is called the peak ground displacement. That is basically the maximum amplitude of displacement at the station close to the earthquake recorded. So there are a number of papers from Diego Melgar and Brendan Crowell and those groups that are showing in this figure here. I hope you can see my mouse, that there is a very straightforward relation between the station and distance from the earthquake source and the peak ground displacement that those stations are recording and the magnitude and size of the earthquake. So by very simple logarithmic relations, we can and knowing the earthquake location from other techniques, we can have a rapid way to estimate the magnitude of the earthquake that then, of course, will influence the size of the, if the earthquake is tsunamigenic, the size of the tsunami. Okay, so here in New Zealand, many before me have already addressed the issue of us living in the ring of fire, and New Zealand basically sits on a tectonic plate boundary. It's quite interesting because we have the Pacific plate that I don't know if you can see this cartoon here. The direction of the subduction interface changed from the north to the south of New Zealand. So we have this direction here, this direction here. I would love to use my hands, but I can't. And then around the central New Zealand, there is a strike slip and the transition between those two different subduction direction. And New Zealand has basically is affected by all the geohazards you can think of: earthquake, tsunami, volcanoes, and landslides. So it's a country that is very prone to geohazard and risk. So a bit more than 20 years ago, two government agencies and GNS Science has established what was called at the time the GeoNet project. That's the same name as the Japanese network, but I will use it to characterize the GNet sensor network here in New Zealand during my talk. And the partnership through those government agencies basically thought that they were thinking that funding research infrastructure that better understand the dynamic and tectonics of New Zealand would have in the long term saved life and economic loss for the country. In 2018, if I'm not mistaken, this GeoNet project became a program. So the government and the agencies that are acting as the government on behalf understood that this program was not a short-term project. It needs to be a long-term endeavor funding for the government. So, and the research infrastructure that was built at the time was mature enough to establish a 24/7 monitoring center that is now operating here in New Zealand and is providing critical information to the National Emergency Management Agency for New Zealand. Another policy that I would like to present here as one of the main thing that has been successful for our GeoNet program is that the New Zealand government in about 10 years ago established, or slightly longer than that anyway, established some policies for government data that at its core has, wherever possible, data needs to be open and available. And that's, again, an economic return from the country. So thanks to that, we've been able to build a multi-domain geophysical infrastructure. That's what we call the GeoNet network. It's a network composed by sensors that cover different domains. GNSS is one of those, but we have seismometers, storm motion, tsunami gauges. Recently, we have now introduced deep DART buoys for deep ocean assessment for tsunami monitoring. We have volcano cameras, and we also are starting to install some what we call envirosensor to measure geochemical changes on volcanoes and landslides. This infrastructure is made of about 1,000 sensors right now, and all the data are open by default. As soon as we receive and collect and archive the data, we make them available to scientists across the globe. And that's probably the success of our program and of GNS Science, of course. I will focus from now on the GNSS network that is part of this multi-domain geophysical network. We have about 200 stations across the country. The network has been and is still run in partnership with Land Information New Zealand. That is our possibly strongest link to the IGS community. We operate 7 stations that are contributing to the IGS infrastructure and real-time service. And then if you look at the network, basically those all the sessions in color coded are currently streaming in real time, and anyone after requesting for some authorization to access some credentials can get the data and use them. Within the GNS Science and the GNS program, we have been using GNSS data to monitor geophysical phenomena at different spatial and temporal scales. So in this diagram here, it's representing different geohazards and their scale. And basically with GNSS, we can look at seconds and minutes. This is an example of what we have recorded after the Kaikoura earthquake, which was a magnitude 7.8, if I'm not mistaken. We have done in 2012, we have used some novel, at the time, applications of GNSS data that are using the signal to noise ratio to understand if a volcanic eruption has some ash in the plume, and this ash will disturb the signal between the GNSS station and the satellite path. We don't have anything operational that is using this technique right now, but that's an interesting one to look at, particularly if you have a volcano that is not fully equipped with all you need to understand if there's some ash component in the eruption you're observing. Then we have some very interesting phenomena in New Zealand. I'm not sure how many of you are familiar with that, but anyway, we have some what is called slow slip events, which are basically earthquakes that can be up to an analog of a magnitude 7 or 8, but that happens very slowly. And we have some areas of New Zealand when those slow events will take like a few weeks to develop. This is in the portion where the subduction interface is a bit shallower, and then towards the region here where the subduction interface is a bit deeper, we observe similar phenomenon, but they can take months to fully develop. We actually have one right now. Those are very important to understand, to study, to understand the potential for large ruptures on the subduction interface in New Zealand. And I cannot spend too much time on that, but that's very interesting science that is done with our GNSS observations. We also have landslides that are moving very fast. So this plot here, I'm not sure if you can see the number, but this is a site that we have to monitor a landslide in the South Island that is moving meters per month, basically. So this one is, if you see from the initial installation of the station up to the end, is moved like 60 meters in less than 2 years. And those are more projects focused to understand dynamics of the of those such landslides. And then the traditional and classic use of daily solutions using that will inform, together with other data, will inform the national seismic hazard model. Okay, so in terms of rapid response for significant events, and with that I mean anything that is probably higher than 7.5, I'm going to use the example of an earthquake that is close to us, so Kaikoura, that happened in 2016. And this is a snapshot of the information that we were able to gather 2 hours after the earthquake occurred. So we have, those triangles are showing the GNSS station that we had at the time. We receive data in real time, but we don't process anything. We just receive the raw data, and all the light blue data we're providing stations every hour, data every hour, sorry. So after a couple of hours, we were able to manually generate the displacement. At the time, if you see this box here, we thought that the earthquake was 7.5, so we underestimated the real magnitude of about 0.5. The earthquake was generated here, and we didn't know until 2 hours later that the rupture was extending up to here. This earthquake generated a tsunami. Back to the application of peak ground displacement. If we had a system in place at the time that was calculating from real-time GNSS the peak ground displacement, we would have probably been able to understand or at least have some hints that the magnitude was underestimated. This is a paper from Brendan Crowell and others in 2018, where they simulated what a system that I will show more in detail later on would have been able to do just using the real-time stations that we had at the time. And in a few minutes, I would say, we would have seen a large peak ground displacement. And if you see here, those dots are all the PGD measured at each station, and those are all basically around this magnitude 8 sites. What you do with that, once you have seismic offset and peak ground displacement, you can basically, on this side of the slide, you can have a rough understanding of the extent of the rupture and the amount of slip that occurred on your earthquake fault. And as others have shown way better than me before, you can use this representation of the earthquake to simulate a tsunami. And in this case, that's again the simulation from the same paper, and they show that this earthquake was very complex. This is not the final fault that we understood generated the earthquake, but still even a rough estimation and understanding of the size and extent of the earthquake were able to reproduce those red dots are the tsunami recorded at tide gauges, and the blue line is the simulated model, and they are at least saying useful to say where the largest impact will be. Luckily, no one was living there, so we didn't have any casualty for the tsunami, but in case this site was more populated, then that would have been a problem. Okay, so as I was saying, for now we have very nice infrastructure. We have and not a very dense, but dense enough possibly network that produce data in real time. But at GeoNet at the moment, we don't process this data. We don't use it. So a couple of years ago, we started a project, an endeavor fund that is called RSET. RSET stands for Rapid Earthquake Source Characterization. And this project has contributors from all over the world and from GNS Science and different research aims. The one that I will focus on is the one that will try to look at the improving and making more rapid the analysis of local earthquakes, large local earthquakes. So with that, I mean anything that is within the New Zealand territory. For the GNSS component of this project, our plan is to use our data and possibly everything that is available from our countries nearby, establish a processing system that will use IGS products, either real-time or long-term data products. And then the idea is to use a software that has been developed by Washington University that is called GFAST, and is used within the US Shake Alert program that used GNSS waveforms to rapidly determine the peak ground displacement, the centroid moment tensor, so the earthquake characteristics, and then use a fault catalog, a predetermined fault catalog to understand and try to estimate the earthquake source and the slip distribution. Some people, many before me, has already mentioned the need to have processing softwares basically that are available. So within our project, the idea is to test some open source software. We cannot test everything, but so we selected 3 that we want to trial. We have some challenges in New Zealand, and one is that we have ocean all around, so we don't have a good system to have a reference frame or some portion of the country that we can consider as not moving. We are sitting basically on a plate boundary, so that's a big challenge that we have. So the idea is to test different real-time processing strategies and see what works best for us. Those solutions will be compared with the system that they have already up and running in USA, the Shake Alert, and I'm collaborating with a number of people, including Simon that was talking today. I'm really grateful to all of those brilliant scientists that write the code and share it with the community, because that's an important piece of the puzzle, I think. Yeah.
I'm sorry to interrupt. Is it closer to your conclusions? We're running towards the end of
Okay, I can skip this one. I'm almost finished. So I will just, that's a slide that was provided by Bill Fry, which is the program lead for the ERSET. What he did here was to, considering the current existing GNSS stations, not just those in real time, understand if we have all of them in real time, can we forecast within 10 minutes, which is a UN mandate, and notify impacted coastal communities of an incoming threat from a tsunami. So all these colors here are representing the number of population, and I don't know if you can see it, but the different symbol is representing if we can successfully send a warning message or not. And as you can see, all these red circles are areas where, based on this simplified approach, where we think we probably are lacking the infrastructure necessary to send a warning message. So I'm closing here, and I would like to thank John Labrec again, because he's trying to connect the dots here in the Southwest Pacific, and that's probably his last slide that he didn't have much time to show, so I'm quite pleased to have the opportunity. John is organizing a first meeting between different people, me included, and I hope that Viljami, Andri, and others that talked today will be able to join. So please reach out to him if you want to try to do something for this region that is beautiful but very risky. Thanks a lot again for this opportunity.
Thank you very much, Elisabetta.